Okay, good morning, everyone. Let's get started. Thanks for braving the weather and making it in this morning. Couple housekeeping notes. Today, after class, I am driving down to Boston. The AAAS, which is the American Association for the Advancement of Science, is having their annual meeting. I will attempt to drive down there and participate today and tomorrow, which means that I will not upload the recording for today's lecture until about mid-afternoon, and the same thing with the quizzes. So they'll be a little bit later, a couple hours later today, and then be back in time for class on next Tuesday. Okay, that's what's happening with me. What's happening with you? Some of you are tackling assignment 5. Some of you are tackling assignments 9 and 10. Any questions about the assignments? All good with PyBullet, PyroSim, your own code? Okay, all right. Okay, so we're making our way through the admittedly brief history of evolutionary robotics. This idea to try and borrow what we see out in nature, which clearly has made a very large number of autonomous and safe machines. Can we take that evolutionary dynamic and incorporate it into machines? An idea that had been around for a long time, actually, but it was only until about the mid-90s that robot hardware arrived that could make this possible. And we're going to finish Lecture 7 today looking at the first 2 experiments of evolving robots that took place in Switzerland and England, respectively. And then we'll tackle Lecture 8, where we're going to take a bit of a digression and look at a particular type of neural network known as a CTRNN, and we'll talk about what CTRNNs are in a moment. Why are we going to talk about CTRNNs? Because they were used in another set of initial experiments in the field, and these were known retroactively as the minimal cognition experiments, which we probably won't get to today, but we'll talk about the CTRNNs, which is a particular type of neural network that are inside the minimally cognitive agents. Okay, so back to the mid-90s, and we started last time talking about this Rube Goldberg-esque contraption known as the Sussex gantry robot. A lot of odd things about this machine, including its 2 motor systems. The 2 motor systems control the 2 trolleys that move across the top of this empty table. We've got this inverted periscope that's hanging upside down under the table, and there's a spinning dental mirror to allow the camera to capture a continuous feed of 360 degrees around itself under the table, which is what is represented by this little square here. We ended last time by looking at foveal vision. So the researchers had a camera on board the robot that was providing a continuous visual field, but there was no neural network on Earth in the mid-90s that could digest thousands of raw pixel values. So the researchers had to come up with some way to compress the information in this raw video feed and throw most of it away, to provide some small subset of visual information into the neural network that's going to control this robot, to allow it to do things like avoid obstacles and move around under the table and so on. We saw this odd way that they did it last time, which is to drop 3 circles of different sizes at different places inside the visual field. Grayscale all of the pixels inside these 3 circles, and then finally take the average grayscale value of all of those pixels inside the 3 numbers, and then finally discretize that average into 16 different bins. 0 for pitch dark and 15 for bright white. So ultimately, at the end, the neural network is going to receive 3 visual sensor neuron inputs, 3 numbers, 3 integers between 0 and 15. Seems like an odd way to do things. Yes? 16 bins? Sorry, 16 bins. Yes, 16 bins. That's right. So part of the reason why they did this is this was through bioinspiration. This is actually not that different from how your eye works. You are not making decisions from moment to moment based on all the raw visual information that's coming in. Your brain either can't or it just doesn't do it. You're using a very small subset of that information from moment to moment. The tricky thing, and this is a problem with feature engineering in general in machine learning, is was this a good choice? Was putting a circle here, here, and here in the visual field sufficient to capture whatever information is going to be required by this robot to move around and do whatever it's going to do? The short answer to that question is probably not. So they've arbitrarily chosen they're going to use three fovea, three foci of visual attention. Were these good choices of position? Are the sizes a good choice? Did you have a question?
Yeah, are the positions fixed or were they random for everyone?
Were the positions fixed or random? What do you think, given all this lead up to foveal vision in this experiment?
I feel like they would be fixed.
They would be fixed? Okay, we could fix them. Let's fix them to this. And now let's evolve this physical robot for days or possibly weeks. Seem like a good thing to do? They were evolved. Okay. I'm giving away my own punchline here. Okay, so this is the first experiment we've seen so far where the evolutionary process is not just going to be tuning the brain of the robot. It's not just tuning the synaptic weights of the control policy inside the robot. In this one of the very first experiments, the researchers are broadening the reach of the evolutionary algorithm. This evolutionary algorithm is going to tinker with or try and optimize the synaptic weights of the control policy for this robot and the positions and radii of these three receptive fields. Fovea and receptive fields are synonymous terms. They're going to let evolution figure out where to punch out small subsets of visual information from the raw visual stream. And by setting the radii of these circles, it's going to allow the evolutionary algorithm to figure out how much visual information to grab. Okay, again, I'm deliberately hiding all the fun stuff from you. We'll see it in a moment. What do you think evolution does? I haven't even told you what the task is, but it's running around under the table, moving away from sub-objects, moving towards other objects. What's a good choice for the positions and radii of these circles, do you think? Is it an intuitive problem? Probably not, from the fact that they evolved it in the first place. But if you think about it for a moment, it seems like you would want the robot to see as much as possible. Why not make three big circles that try and capture as much of the raw visual field as possible? Seems like a good thing to do. Why would you partially blind the robot by making small circles?
Then it's getting more detail because the average is over the entire circle. So if you have a smaller one, it's like you have more information about that point.
Excellent. So if the circle is very big, then we're averaging over a large area and the robot is getting a global but blurry sort of image, which again is not how you tend to do things, or at least actually you do get mostly a blurry image, and then small resolved detail in certain places wherever these small visual fields are. But if these receptive fields are too small, then we're overly blinding the robot and probably not a good thing to do. So it's a Goldilocks problem. There's probably somewhere in between. There's some sort of intermediate size that these receptive fields should be, and also they should be distributed probably not all on top of one another, because that would be a waste of information. You want to spread them out, but spread them out how? If you think about it for a little bit, you can start to see there's probably already a bit of a tension here. Not too big, not too small. We want the receptive field spread out, but maybe not too spread out. As always, artificial evolution, like biological evolution, is trying to strike a balance between competing desiderata. This is part of why there is no optimal organism in nature. There is no one optimal solution. All of us and everything out there is a differently struck trade-off between different desiderata. Okay, sorry for the long build-up. Okay, let's get into the experiment. In this case, they started simple. And by starting simple, I meant that when they ran their evolutionary algorithm, they ran it in an incremental fashion. Everything we've seen so far, all the evolutionary algorithms we've seen so far, we start with a random population and we evolve that population for a bunch of generations against one and only one fitness function. In incremental evolution, we do the same thing. We create a random population of solutions and we start evolving them against one fitness function. But as they get better at that fitness function, we change the fitness function. We change how the evolutionary algorithm decides who to kill off and who to make randomly modified copies of. Okay. In incremental evolution, you usually start with a simple fitness function, meaning it doesn't take long for the evolutionary algorithm to evolve robots that start to solve this simple problem. So what's the simple problem? They're going to take each random set of weights in the population. We've got a population of neural networks with weights, and we have the position and radii of these receptive fields also. So our genome is made up of all the synaptic weights plus positions and radii of the three receptive fields. We take each one in turn in the population and drop it into the robot, move the robot to a random position under the table, turn on the neural network, allow the gantry robot to do its thing for a few seconds, stop the robot, then move the robot to a different initial position, and with the same set of synaptic weights and the same three receptive fields, turn on the robot again and allow it to move again using the same brain and the same visual system. And then we're going to average how well the robot does over a number of these individual evaluations. So far, so good? Okay. What do they want it to do? Not that complicated. No matter where the robot starts under the table, they placed a big black piece of Bristol board underneath the table. So in theory, the robot can see there's a black patch in one part of its visual field and nothing or bright colors everywhere else. And all it's got to do is go to the back wall, go towards the black patch at the back of the table. Okay. After they evolved for a few hours on the gantry robot, and eventually they get success. No matter where they put the gantry robot, it always drives towards the back black wall. Okay. Now they paused evolution, so they've got a population of sets of synaptic weights and receptive fields, and now they change the fitness function so that it will approach a back rectangle from 4 different initial positions. So now they cut out from the Bristol board a black cube, and they place it either in the back left or the back right underneath the table and turn the robot on, and it has to move towards that black patch underneath the table. Again, not that difficult. After a while, the robot evolves to do that. In the third and final phase of the evolutionary process, they swap in a third fitness function, which is underneath the table at the back. They either place a black rectangle back left and a black rectangle back right, or the black rectangle back left and black right, and the black rectangle, black triangle back left. Did I get that right? The back of the table. Okay. Wherever the robot is placed, it needs to go away from the rectangle and towards the triangle. So a lot of build up to this problem, but they're basically evolving this robot to distinguish between triangles and rectangles. Okay. Let's have a look at the 3 fitness functions that they swapped in during this evolutionary process. We have uppercase Y-I here. Y is the distance, perpendicular distance away from the back wall. So if the inverted periscope drives to the front of the table, that produces a large yi. If the robot drives to the back and is touching the back black rectangle, y sub I is 0. It's a little confusing because in this case, in this particular evolutionary algorithm, they're trying to minimize the value of the fitness function. This is kind of an annoying feature of this research community. Sometimes they're maximizing their fitness function, sometimes they're minimizing it. Doesn't matter as long as you keep it consistent within the experiment. Question?
I think this question is a little trivial, like it doesn't really matter, but does the robot know that, like, what a triangle looks like, or does it just know that this is the rectangle, just go to the other black part of the wall?
It is absolutely not a trivial question. Does it recognize the triangle or the rectangle? It's the whole point of this experiment, which we're kind of delaying.
Okay.
You obviously all know that that's the door. You recognize the door and you know to go there when time is up. It's obvious, right? You see it, it's a rectangle. Why are we even bothering talking about it? Is that really true? Thinking about thinking is misleading. You're going to see in a moment, we'll look at the evolved results, and I'm going to ask you exactly that question. Does this robot recognize or know what a triangle is or a rectangle is? Actually, it's a very good question. Okay, so in this case, we're minimizing the fitness function. Remember our fitness landscape when we talked about evolutionary algorithms. When I introduced it, we were talking about maximizing fitness, climbing higher and higher in the vertical fitness axis. When we're dealing with an evolutionary process that's trying to minimize fitness, it doesn't really matter. It's a whole bunch of points in the space of all possible robots, and those points are trying to climb down into the lowest possible depression or swim into the deepest oceanic trench. Get as low as you can. We're dealing with distances in this experiment. Distances by definition are always positive, so the lowest you can go is 0. The optimal fitness is 0. Everything above that is not as good. Everybody oriented? Okay. You'll notice that the fitness function is a summation over 4 evaluations. We're evaluating every controller plus the fovea 4 times, and we're starting the robot from random initial conditions for obvious reasons. We want to see how this robot does on average. It might get lucky. We might put the robot at some random initial position for which that neural controller knows how to drive the robot towards the back wall. In general, in evolutionary robotics and machine learning in general, we usually evaluate a solution a bunch of times in different randomly generated versions of the problem we want to solve, and make sure that the machine or the robot can solve that problem in general, on average. Yeah? Okay, not that complicated. Once they get this value pretty close to 0, it's never going to be perfectly 0 because we're dealing with the real world here. They swap in the second fitness function, phi2 here. Now we have di, which is the distance of the robot from the center of the rectangle. So they actually are evolving these controllers not just to go to the rectangle, but drive to a particular position, the center of the back rectangle. Third and final one, a little more complicated. We're still summing over 4 trials, so we still want good average behavior. You'll notice there's 2 terms now. We're subtracting the second term from the first one. Remember that we're trying to minimize this fitness function. So if we take one term and subtract it from another term, is the first term, are we trying to reward high values for the first term or penalize high values for the first term? Are we trying to reward behaviors that maximize the second term or penalize high values of the second term? Unfortunately, a lot of evolutionary robotics, we're going to do a lot of these double, triple negatives.
Can you go to a negative?
Can it go to negatives?
Yeah.
You'll notice that within the terms are all D's. So the D's are a reminder that we're dealing with distance, different distances, but distances are always positive.
But like if the first value is smaller than the second value,
Then you could get a negative.
Yeah, like and
Absolutely. So now we can get negatives and positives. Absolutely. Okay. So we're dealing with negatives and positives here. You can read off what the definition of these variables are in the first term. What is the first term evolving the robot to do? Imagine there was no second term and we just evolved phi3 with the first term. What behavior are we evolving for in the first term?
Moving further away from whichever object 1 is.
So whatever object 1 is. So d1/2, distance of rectangle / triangle. So 1 is for rectangle, and 1 is for rectangle and 2 is for triangle. They should have just used R and T, but there you go. Okay, so D1I, uppercase D1I, distance of the rectangle from the start point. Okay, so they're normalizing here. When the robot starts at an initial position, uppercase D, they want to see the difference. Yeah, so the robot starts this distance away from the rectangle, and the robot ends this distance away from the rectangle. What is it we want this first term to be? We want this to be as small a number as possible, right? We want lowercase d1 to be really big, be as far from the rectangle as you can at the end of the evaluation. We want this term to be as small as possible. This one, the opposite. We want it to be as big as possible. Be as close to the triangle as possible at the end. Okay. Seems like a lot of hoops to jump through to go close to the triangle and stay away from the rectangle. But that's in effect what we're asking for. Okay, there's also alpha and beta in there. Why? Why do you think the investigators included alpha and beta? They're weighting terms. These are things that are going to be set by the investigators by hand before evolution starts. Why did they put them in there? Why didn't they just use these two unweighted terms? Why weight them?
Maybe they could weight going close to the triangle more highly than going far away from the rectangle, because otherwise you could just go in a really far off direction away from the rectangle.
Absolutely. So whenever you're reading a scientific paper and there's some additional little detail that's kind of weird and hard to explain why it's there, you can usually guess why, because they probably ran the experiment without that little detail and the experiment didn't work. So they put a little tweak or a little hack in there to get things to work, as we all do.
My guess is it would stay still without any turn.
Possibly.
Like, on average, if those are weighted the same, then staying still would give you a 0, and moving anywhere closer to the rectangle would give you a positive value.
Absolutely. This is one of the things that's been so difficult about AI and robotics for years is pretty good solutions to most problems is don't do anything. If you're not very good at anything yet, because it's still early on in evolution or early on in training, most of the things that you're likely to do are going to make things worse. So evolution and most machine learning algorithms are conservative. They will often get trapped in this black hole of do nothing. And then you got to put something in that motivates them to try things. You have to lessen the amount of penalties, for example, or increase the amount of rewards to push it out of this local optimum of do nothing. Hard to know with the gantry robot. It could have been that. It could have been the unweighted terms that as it went towards the triangle, it just ignored the rectangle and went close to the rectangle, or it was the Bradenburg coward and just stayed away from rectangles and didn't dare going close to the triangle, even though it could sense it. Who knows? They probably carefully set alpha and beta until they got something that went to the triangle and away from the rectangle.
So this is a controller. Are alpha and beta the gains?
They are not gains on the controller. The controller does not have any gains yet. We're going to talk about C tier and ends in a moment, which do have gains. But they are gains in the general sense of like volume knobs. Turn up the reward you get for avoiding the rectangle, or turn it down. That's alpha. Beta is turn up the turn up the penalty for approaching the rectangle, or turn down the penalty for approaching the rectangle. Beta is turn up the reward for approaching the triangle, turn down the amount of reward for approaching the triangle. Right? So we've got a carrot and the stick fitness function here. There's reward for doing one thing and penalty for doing another thing. And we need to balance the amount of reward or penalty, or we fall into these attractor basins of perverse instantiation. I'm just going to do nothing. Or I'm just going to run away from the rectangle and ignore the triangle. Or I'm going to go straight for the triangle, and I don't care if I go very close to the rectangle along the way. Dirty little secret about machine learning in general. There's a lot of these what are called hyperparameters, additional parameters that need to be set so that the learning or the evolutionary process ends up with the solution you want at the end. It's an unsolved problem in both fields. Okay, so far so good? Okay, let's look at some solutions. Again, mid-90s, MP4s were sparse at the time, so we'll have to do with a time-lapse image showing what's happening. We're looking down through the open table, and here's the triangle at the back right of the table, and the rectangle is at back left underneath the table. And if you squint, you'll notice there's 4 trajectories. 1, 2, 3, 4. All of which end up at the triangle, which is good. And this one gets kind of close to the rectangle, but not too close. This wasn't too difficult. What else can you tell me about this evolved solution? So we're looking at one evolved neural network driving the gantry robot, plus whatever those 3 evolved fovea are. It can clearly see the triangle. Not clear whether it can see the rectangle or not. Maybe yes, maybe no. What other observations can you make from this admittedly simple figure? What does the little line segment with the circle in the front mean? Sorry, go ahead.
I was going to say it's interesting that the 3 start points that were close to the rectangle sort of immediately moved away, whereas the one farthest to the left, or I guess to the right, close to the triangles, did the opposite.
It goes kind of towards the rectangle and then veers away. Yeah. Hopefully you can immediately notice this is not an optimal solution. The gantry doesn't do this. We never get the optimal solution. It's always something that's pretty good, and sometimes it's kind of good in surprising ways. What are some other odd features of this solution?
Seems to like making circles.
Odd. Any idea why?
Looks like it can only turn to the left.
It can only turn to, it is only turning to the left. Now, in theory, the gantry robot can turn to the right. It can do all sorts of things, because remember, we've got one gantry going like this, and the other one driving like this on it. So it can move arbitrarily in the gantry robot mechanically can describe any arbitrary 2D trajectory underneath the table. This isn't. There's a subset of trajectories that it seems to like.
It's like getting feedback from the fitness function in real time as it moves away. It's like, oh, I shouldn't do that. I should go back around.
It's a good observation. It could be. In most evolutionary robotics experiments, including this one, there is no real-time feedback from the fitness function. So when the robot is done, The desktop computer to which the gantry robot is connected takes all of the XY positions of the gantry robot and computes the Ds and then finally computes phi 3. But the robot doesn't have that information. The only information the robot has is these 7 numbers. That's what it gets. Yes?
Well, so far, have they only had the triangle on the left side, or have they like moved?
They've switched them all over the place. They don't show it here. They should have. If they switch them and then they replay the robot with exactly this same brain, it will do something similar to this, but end up at the back left of the table. Okay. We're going to see lots of robots in this class, and we're going to see a lot of them that do move in this helicoid motion, this spiral type of motion. At the end of the class, when we get to the xenobots, the little robots made out of frog cells, they move in helical motion. We understand a bit of why all these robots tend to like to move in spirals, but we still don't have a good answer to it. For us bilaterally symmetric machines that tend not to walk like this, doesn't feel like a very good way to do things, but it seems like for a lot of robots, that's not only okay, it's preferred. Not quite clear why. Okay. All right. Again, I really apologize for the quality of this figure. Actually, I love this figure so much. Let me see if we can zoom in a little bit so you can really see what's going on here. Okay. All right. We're looking at the brain of this robot and the eye of this robot. Okay? Here's the raw video feed, and here are the 2 fovea that evolution evolved in this particular case. You'll notice that one of the 3 fovea is missing. Seems odd. I just told you that evolution is allowed to place the positions and radii of 3 circles. It can't delete circles. Where's the 3rd one? Bear with me for a moment. All of the nodes and edges that you see here, nodes represent neurons and edges represent synapses. In this case, they drew the input layer on the left and the output layer on the right. And I just finished telling you that this robot has 7 sensors. There are the 4 binary bump sensors. Was I bumped front left, front right, back left, or back right? And the 3 values, the 3 integers coming from the 3 fovea. There's supposed to be 7 sensor neurons here. There are only 2. Over here, we have the left motor and the right motor, which is a little confusing. I think this is a typo. Left motor and right motor should be the movement of the two trolleys, the X trolley and the Y trolley. And I have yet to figure out what this 3rd neuron means. Doesn't matter for our purposes.
Can you give like a spark notes of the significance of the fovea and what they are?
Okay, so the significance of the fovea, the problem that they had to solve in the mid-90s, they can't take all 10,000 pixel values and plug them into 10,000 input neurons because they couldn't run a neural network of that size on mid-90s hardware. That's why. So they had to squish all that raw value down into a few values, and they said, well, our eyes do that also. All the photons coming in are squashed down by the fovea. You have one here and one here that sit at the back of your eyes. So let's do the same thing. Let's drop some fovea, but we don't know where the fovea should be and how big they should be for the robot. So we'll let the evolutionary algorithm figure out where to place the fovea and how big or small to make them.
Yeah, so how does it, is the visual area that the fovea are placed in, is that just an accumulation of all the sensors?
They are the sensors. This is one sensor,
those are the sensors.
and this is a second sensor. So this, although it's drawn as a circle, these are frames in a video.
Okay.
And the fovea are punching out little bits and pulling them out and pushing them into the left side of into the left side of the neural network.
So this is the video from the camera that can see.
This is the video that's coming from the camera that can see 360 degrees under the table.
So the like frames that it's looking at are at 360 degrees.
The frames are at 360. So here we go. Bear with me. Snapshot, 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 snapshot. Put all those together into one big single image, and that's a view of 360 degrees around myself. Next time step, snapshot, snapshot. Make a second frame. That's what this circle is meant to represent. It's a panoramic view around the robot. And then evolution figures out how to punch out little pieces from this panoramic view and plug them into the neural network every 1/10 of a second. So it's seeing a small bit of its worldview as it goes.
You said that some of the sensors were like the bump sensors, right?
Yep.
Does it have like obstacles to navigate through right now?
In some experiments, yes, but not in. They did many experiments with the gantry robot. In this experiment, they didn't. There was nothing to bump into. It could bump into the back wall, I guess, but it didn't really play a part. Okay, I know it's hard to put yourself in the shoes of the gantry robot. How are we doing? Okay. Okay, so we're supposed to have 7 input sensor neurons over here. We're supposed to have 2 motor neurons over here. Like I said, I don't know what the third one is. Doesn't really matter for our purposes. Here's the one controlling the X trolley here that moves the X trolley back and forth. This neuron moves the Y trolley back and forth on top of the X trolley. These are the 2 movement commands. They did not draw the other 5 sensors here. They are not drawing the 4 bump sensors because the evolutionary algorithm never wired them up. It set the synaptic weights coming out of those 5 sensor neurons to 0. You have 10 to the 11 neurons in your head, more or less, and you have 10 to the 14 synapses in your head, more or less. Not every neuron is connected in your head to another neuron in your head. If it was, that bundle of neurons and synapses would not fit in this building. Just can't do it. So in us, there is selective wiring. Not everything is connected to everything else. Similarly, when we evolve brains for robots and we allow evolution to tune the synaptic weights, often evolution will, through mutation and crossover, some of those weights will get closer and closer and closer and closer to 0 until they're so close to 0 that those sensors effectively have no influence whatsoever on the movement and behavior of the robot. Question?
Because there was nothing in there that it was trying to avoid?
Exactly. The bump sensors, it didn't matter whether the bump sensors did anything, so they atrophied. Evolution just got rid of them. Didn't need them. Again, same thing happens with you in your brain and your body. Use it or lose it.
If there were obstacles, but it still had fitness functions for the experiments that didn't count collisions at all, would it have used the bump sensors?
That's a great question. I have absolutely no idea. Those are the kinds of things you could test in your final project. If it gets the information, if there are things to bump into, but for whatever reason that information is irrelevant to the task at hand, does evolution get rid of those connections or not? I'm a betting man, so I would bet yes, it's going to get rid of them, because if there's information coming in that's irrelevant to what you want, it's probably going to affect your behavior. If the synaptic weights are non-zero, it's going to affect your behavior, and that's probably a distraction. You want to evolve the ability to ignore that stimulus. It shouldn't influence what you're trying to do.
So what you just said, do you mean by that if they did add obstacles, and I'm not sure if this is what they just asked, but that if they add obstacles, then it wouldn't be able to redefine those synapses that it's already removed?
No, this is the great thing about evolution. There's no permanent undo, right? Because mutations could then start to change synaptic weights that are at zero or very near zero and start to make them non-zero again. If there's stimulus that an organism or a machine is ignoring, but from an evolutionary point of view, if it didn't ignore that information, it would be better able to do whatever it is we want it to do. Given enough evolutionary time, mutations would start to fold that sensation back into influence on behavior. Yeah. I would encourage you, once you get far enough in the assignments that you're evolving sets of synaptic weights for your robot, look at the weights. It's very hard to tell what they're doing. You get a big mass of positive and negative floats, but you can look for values that are very, very close to zero. That's usually a strong hint that evolution is trying to get rid of some potential information you made available to it that it doesn't want. Okay. So 5 of them are gone. All 4 of the bump sensors are gone, and one of the fovea has been quote unquote erased as well. This particular robot here is perfectly capable of finding and going to the rectangle with only 2 focused parts within its visual field. It doesn't need the third one. This is the evolutionary algorithm showing off. It says, I do know what a triangle is, and I'm going to show you by always going to it, and I don't need 3 fovea to do it. I just need 2. So far, so good? Okay. All right. Other things to notice about this neural network. The solid arrows are excitatory connections, synaptic weights that are positive, and the dashed lines are inhibitory connections, synaptic weights that have negative values. You'll notice there's a combination of inhibition and excitation here. Kind of cool. What it means, I don't know. The researchers don't know. This experiment is 30 years old. No one's figured it out yet. Okay, cool that it's there, but what else can you tell me about the neural architecture? The way all of these neurons are wired up. What else is going on here?
The 5, 6, 3, and 11 nodes you can only get to from the left motor.
From this motor, it's actually this one, whatever this one is down here. Yep.
But it has to be an inhibitor.
There's an inhibitory connection going in here. It goes into this little neural circuit here. And then there are 2 outgoing excitatory connections that connect to the X trolley neuron and the Y trolley neuron. Okay, yeah, interesting. I don't know what that circuit is doing. What does it mean for connections to be going back and then going forward again? Recall our discussion about neural networks. It's a particular feature of neural networks that exists in some neural networks, not in others. Getting close, there's the back propagation of error, in which error flows backwards.
They're recurrent connections?
These are recurrent connections. And recurrent connections, the way that they operate during forward propagation, as sensor values flow, in this case, from the left to the right, to the motor neurons, the recurrent connections are bringing information from the motor layer back in and then back out again. What do recurrent connections, what do they confer on the neural network? What do they allow the neural network to do? Memory. They allow the neural network to remember. So this is a strong hint. However, this neural network plus fovea is allowing the robot to always drive to the triangle. It's probably using memory. It's remembering what it saw 1/10 of a second before. Okay, if that's not confusing enough, there's also self-connections. This is a recurrent connection that's very local. So what is this recurrent connection doing? It's ensuring that the new value of neuron 4 here, the new value of neuron 4 is a function of the value of 1 times this weight, plus the value of neuron 0 times this weight, plus the value of itself at the previous time step multiplied by this weight. It's holding on to some internal state and combining it with incoming information from these two sensor neurons, which are connected to the two fovea. It's remembering stuff from before. Okay, confused yet? Okay, all right, back to your question about does the robot know what a triangle is and a rectangle is? Where is the recognized triangle subroutine or neural circuit in here? Where is the recognized rectangle neural circuit in here? It seems to know what a triangle is. It always goes towards it, regardless of whether it's on the left or the right. How? How is this robot recognizing a triangle and possibly distinguishing it from rectangle?
I'm not 100% sure how to put it, but I think it could be using some of the recurrent connections to look at where the two shapes, like where the borders are and how those borders are shaped, because it's going around completely, so it will notice that a triangle is going to have different, there's going to be a different point where it gets darker, darkest, and then later, versus a rectangle.
Bingo, exactly. Okay, excellent explanation. There was a lot of pieces in that explanation, which is exactly the point. As you noted, first of all, the robot is going around and around, this helicoid motion. We understand some of why it does it. Part of why we understand that it does it is it's turning around and around and around, which means patches of darkness are sweeping across this raw visual field, which means, remember that we are averaging the darkness within these two fovea. So as it's turning and it sweeps across the rectangle, at some point these two fovea are going to go dark, and then as it turns and passes by looking at the rectangle, they're going to brighten again. So far, so good? So our explanation of what a rectangle is or what a triangle is from the perspective of the gantry robot is first of all dependent on the way it moves. If I ask you to describe a door, few of you would probably say the edges of the door get bigger as I approach it. That's not usually how we tend to explain a door. We say, well, a door is kind of a rectangle. We tend to drop the motoric aspect, the motor aspect, the behavior aspect of the explanation. Remember BabyBot that was squishing grapes and different fruit in front of it? All of its explanations for what an apple was or a banana was or what self was had a motoric component. When I move or when I send commands to motors 4 and 7, I see motion. When I stop sending commands to motors 4 and 7, the blob disappears. That's my definition of self. It's a sensor-motor relationship. I do this, and the world pushes back in this way every time. That relationship is what self is, and what an apple is, and what a banana is, and so on. Similar explanation here. Question?
So that third, motor neuron.
Yep.
Is that controlling the direction of the mirror?
Okay, thank you. Yes, it's good question. Now I remember what this third piece is. I told you when we started talking about the gantry robot that the dental mirror is spinning around and around and around underneath the gantry robot to make this 360-degree view. That's true. To make this more confusing, the camera itself can twist. I forgot. There is a third motor that's turning the camera, which is also very confusing because the camera is getting a 360-degree view, but the orientation of that 360-degree view is altering as the camera turns about the long axis of the periscope. Okay, let me act this out for you. Take a picture, 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 take a picture. There's one 360-degree view. I have a panoramic view of this room. So far, so good? Then I move, and I, as the camera, move, and I turn. Take a picture, 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 take a picture. Now I also have a second panoramic view, but it's oriented differently. I started taking pictures at a different position. Make sense? That's what the world looks like to the robot. That's what the third motor neuron is. It's turning the camera underneath the table.
Importantly, that changes what's under the fovea.
That changes, that's what causes blobs of black to sweep across the fovea and darken the fovea, and then the fovea go bright again. I'm sorry, I missed that very important piece. Everyone got it? Okay.
Is there a rationale for why they initially tried 3 fovea?
3 is a good number.
Because I'm just thinking, like, I don't know in nature that there are any like animals with an odd number of eyes. 2 is the most common, but it's almost always even numbers.
Correct. Yeah, seems like kind of an arbitrary choice. I think they just picked something. I know these researchers pretty well. I should probably email them and just ask them. Assume it's arbitrary for now. Okay, so coming back to your explanation of how this controller on this robot solves the problem, you can imagine as it's doing its weird dance here, as it's moving and turning, the fovea are darkening and brightening. And the last piece, I think, of your explanation, it was about the time at which this happens. Imagine the robot is turning and the black rectangle sweeps in from the left and leaves, well, it never leaves its field of view, but sweeps from left to right along its panoramic view. At some point, fovea 1 goes dark, and then a short time later, fovea 2 goes dark. And then as things continue, at some point, half a second later, fovea 1 goes bright again, and then fovea 2 goes bright again. There's a time interval between the darkening and brightening of these 2 fovea. You'll notice that they're not lined up vertically and they're not lined up horizontally. They're diagonal to one another. Tell me about the triangle. What happens if the triangle sweeps across these 2 fovea? What's the same and what's different?
It will be a similar thing of first 1 goes dark and 2 goes dark.
Let me just pause you for a moment. So that's the point that's the same. Both fovea, one's going to go dark, and then the other one's going to go dark. They're still going to do the same thing, but
there are, depending on the exact placement and the exact shape of the triangle, it's possible that like the both start to get lighter at the same spot if they're at the right diagonal angle, such that they hit the edge of the triangle at the same time.
Yep.
But also it will be a different period of time for them to start brightening versus the rectangle.
Excellent. That's it, right? So it could be that if the triangle has this angle, both of them go dark at the same time. Could be. In which case, there is no time interval between the darkening of 1 and the darkening of 2. Maybe it's a slightly different angle, so the timing is a little bit different. But the time interval between which the 2 fovea goes dark is different for the triangle and the rectangle. Everybody kind of see that? That is the difference between triangles and rectangles for this robot. Not that triangles have 3 sides and they have inner angles that add up to 360 degrees and rectangles have 4 sides and blah, 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 blah. That's not the answer for this machine.
This is like a question is about the experiment.
Sure.
They always use the same shape and orientation of.
Do they always use the same shapes and the same orientation? I don't remember, and I don't think they said in the paper. It's not quite clear. So it's very possible that they put in a different triangle, and the robot says, I don't know what this thing is, and it either does go towards it or it doesn't. Nothing here about how well or poorly this robot generalizes.
Were the foci randomized or initialized randomly?
They were, at the beginning of evolution, they were random numbers, like the set of synaptic weights were random. Remember, the genotype is the blueprint for the robot. So in this case, the genotype or the blueprint contains at the beginning, contains randomly generated numbers for all of the arrows that you see here, and an additional 9 random numbers. The X and Y coordinates of the 3 fovea, which is 6 numbers, and then numbers 7, 9, 8, and 9 are the 3 radii of the fovea. So yes, the placement and size of the fovea was random at the beginning of evolution, but we are now at the end of evolution. This is an evolved controller plus an eye that works. This is no longer random. Yes?
Can you explain again why there's different values for the triangle and the rectangle, color-wise?
Sure. Okay, so let's imagine there's a big black rectangle at the back of the room, okay? And I've got fovea here, fovea 1, fovea 2, and I start moving like this. There's a big black rectangle at the back of the room, so fovea 1 goes dark, and now fovea 2 goes dark because they're pointed onto the rectangle. And then as I continue moving, this one goes bright, this one goes bright. So there's a time interval between these events. Now imagine there's a triangle at the back of the room. The time interval was much shorter. That's the difference. I'm glad you're asking all these questions. It's very non-intuitive, but it's very important. This robot sees and understands the world differently from us, ? Because for us, that's not a triangle or a rectangle. This is a rectangle, this is a triangle. Or is actually the way we distinguish between things in the world much closer to this, but we don't know it. We lie when we explain what a rectangle and a triangle is.
Is it seeing, the way that we see it is top down, we see the rectangle, the square, the rectangle, and then the triangle, the point is the top, but how is it? Oh, it's viewing top.
It's not specified here whether the triangle is this way up or this way up.
So if it was looking at the point, then it would still just be kind of seeing it flat. It wouldn't understand the dimension of it.
Could be. I think the way it's set up is the 2 fovea will always go black at some point. It can't see the tip, and this one misses the rectangle. It's a good point. It's a detail that doesn't matter too much for our purposes today. Yes?
If the mirror is spinning 360, why does the camera also?
Because the orientation of the panoramic view changes or can change as the camera rotates. So it's a good question. Okay. All right, let's talk about the big circle for a moment. This is the panoramic view of this room, okay? And imagine at this time instant, in my panoramic view that I capture of this whole room, north, or this part of the panoramic frame, this is one image at a point in time, starts there. And then the panoramic view unfolds like this. So far, so good? But if I move and the camera rotates like this, so I'm now pointed into the back corner of the room, and now we start stitching together this panoramic frame, a tenth of a second later. Up here is going to start with the back door and then go all the way around back to the door. So imagine a whole bunch of circles stacked on top of one another, where every circle is the panoramic view, and the stack is the video. All of these panoramic views stitched together. They're oriented differently if the camera is rotating, which causes, in effect, objects within that panoramic view to sweep past the fovea, which are being punched out of this disc, out of the panoramic view. Everybody see that? I need to build a prop for this lecture, clearly. It's tricky. You can think about the world spinning or rotating from the robot's point of view, but the fovea stay fixed. So patches of black and white are sweeping across the fovea. That's really the most important thing for us to take away from this lecture today. The time at which these things go dark differs for the rectangle and the triangle. The robot needs to know those time intervals in order to know, am I looking at the triangle or am I looking at the rectangle? How does it know? How does this robot know the time intervals? What does this neural network need to be capable of in order to know about time intervals?
It has to remember its previous states.
It needs to remember its previous states. That's what at least some of these recurrent connections are doing. They're holding on to some information from the fovea at previous time steps and combining it with values from the current values of the fovea and looking at differences. And in that way, it can indirectly compute time intervals and know what to do with the black blob that's currently in front of itself. Question?
Wouldn't this mean that this is reliant on the triangle and the rectangle being the same size?
It probably, they are the same size, and this whole solution has probably evolved to be specialized to that. We could run the experiment again and place differently sized rectangles and triangles. This is, although it might not feel like it, this is still a simple experiment, right? The robot isn't doing anything very complicated.
Because I feel like it would make more sense rather than there being time intervals between when both go dark, when there's a steeper gradient with the triangle, because the triangle goes to the point and the rectangle just has like, and
Okay.
especially if it's moving in this direction and the triangle goes like this, like.
Could be. It could be. Thinking about thinking is misleading. If we're dealing with larger and smaller rectangles, this strategy can still work. Both fovea go dark because they hit the right edge of a big rectangle, and they stay dark for a long time interval until they go bright again because they're sweeping across a big rectangle. Now they're presented with a small triangle, and they go dark at the same time, but they stay dark for a shorter period of time during motion. Aha! This neural network or something similar to it could distinguish between those time intervals, darkening and brightening. Maybe this thing could learn about big and small in that way. That principle would still hold for big and small triangles. There are ways in which this robot or this approach could still deal with differently sized objects, differently shaped objects, but it doesn't feel good. It's not the way we do it, or it feels like the way we do it. All good? Okay. Question?
Wouldn't it also be the case that it doesn't even necessarily have to just use the time intervals that both sensors were dark versus light, or it could use like comparing the time intervals. Oh, I'm not sure how to phrase this. But basically, so for a rectangle, sensor 1 and sensor 2 will be dark for the same amount of time because there's not going to be any difference in where they're hitting the boundary, but for a triangle, it will be different. So couldn't it theoretically use that to tell instead of just, is it bigger or smaller?
You could also use that. There are other solutions. You're getting it. This is it. This is a different way of thinking about how to grapple with what's out there in the world, even if what's out there in the world is just black triangles and rectangles. There's different ways to do it, or at least different from the way we feel like we do it. Tricky. Most of us in the West are trapped in Cartesian thinking. There's the body and the brain. We sit passively and we do geometry to figure out that's a door, that's a chair, that's a human, and so on. If you forget all the details we just talked about now, the one thing I want you to remember is the explanation of however this thing is discriminating between shapes. That explanation contains the following ingredients. Movement. The robot is moving and the camera is turning. Time intervals between going black and going white. So movement, time, sensation. The fovea goes dark, the fovea goes bright. The explanation has to do with physiology. Where are the fovea? How many fovea are they? How big are they? Is it using the bump sensors or not? Movement, time, physiology, sensation. Memory, the cognitive parts, it needs to be able to remember things. All of those go together, and those pieces of the story combine little bits of body and brain. This robot doesn't solve the problem through the sheer force of its brain alone, and the body doesn't matter. The body matters. It depends where the fovea is. It depends on how the robot moves. Cognition for this simple creature is a result of body and brain all mixed together. This is a non-Cartesian approach to understanding intelligence. From my perspective, this was us in the West 300 years later starting to crawl out of the Cartesian black hole, starting to realize there's other ways that we may be able to reason and grapple with the world around us. Okay, thank you for your patience while we spend quite a bit of time on the gantry robot. We have all of 8 minutes left to introduce CTRNNs in lecture 8. So we'll just start in and we'll finish this off next time. Okay, what does CTRNN stand for? It stands for continuous time recurrent neural networks. Hopefully neural networks is a familiar phrase to you now. We just talked about recurrent connections. So CTRNNs have recurrent connections in them, but CTRNNs unfold continuously in time rather discretely in time. This is something you've probably not seen even if you've taken a neural networks course before. We are creatures that exist in continuous time. Maybe we should be armed with neural networks that also unfold in continuous time, or maybe our machines should be. All right. If we start talking about continuous time, we have to avail ourselves of our very old and familiar tool of calculus. Bear with me, the only place we're going to see calculus in this class. Okay, let's start with y equals mx plus b. Hopefully you remember this from high school. M is the slope. It describes the relationship between how y changes as a function of x. All good? Okay, no frightened expressions. That's fine. All right, we're not going to look at x and y. We're going to throw x and y away and replace it with t for time on the horizontal axis and x on the vertical axis. Okay, which just gives us x equals mt. M is the slope, which tells us how does x change as t unfolds, as time unfolds. And you know how to calculate the slope. It's the difference between two values of t and two different values of x. No problem, we can calculate the slope. But what happens as delta t starts to approach 0? As we want to know how time changes continuously, not how time jumps from 1/10 of a second to the next continuously. A lot of folks hundreds of years ago were scratching their head and be like, well, wait a second, slope is ill-defined as delta x and delta t go to 0. So how do we deal with this? Okay, what did they have at the time? They had difference equations, which allowed them to describe how things change over time in a discrete manner. Whatever the value of x is at time t, they could write down for some systems, well, they knew what the new value of x would be at time t plus 1. It would be 1 more than whatever x sub t was. That's a difference equation. As we take one step in time, as we go from t to t plus 1, x also changes by 1. No problem. Yep?
The fact that you're adding 1 to x, like the fact that you're adding 1 to t makes this discrete.
This is discrete. Difference equations, this is what we had before calculus. This is all that we had before calculus, right? We could only describe things discretely unfolding in time. But increasingly, there was a need to describe things changing continuously in time, right? So, okay, well, why don't we just take difference equations and just shrink the interval and keep going? You probably, maybe, hopefully you remember, things get weird pretty quickly. It doesn't work. You can't do this. So we have to invent something else. So let's invent something else called the differential equation that doesn't fall into this trap. And we're going to describe it as dx over dt. As t changes, how does x change? As we go on, like most mathematicians, I'm going to be lazy and we'll just write this as x prime. Right? Wherever you see a prime, that's a reminder that we're not dealing with the value of x. We're dealing with the value of how x changes, and usually how x changes over time. All good? Everybody remember? Okay. All right, off we go. Okay. When we looked at equations describing how neurons change from one time step to the next, we sum up all the incoming values and squish that sum through an activation function, and then do it again a short time later. The mathematical description of that process was a difference equation. We were describing how neurons change their values discretely in time. We don't want to do that now. We want to be able to describe how a neuron's value changes over time continuously. Okay, so how do we do that? We're going to have to use differential equations. Okay, so in a CTRNN, we take all of the neurons inside that neural network. Let's say there's 13 neurons inside in a given CTRNN. We are then going to describe the behavior of that 13 neuron CTRNN as a set of 13 differential equations. Yeah? Okay, so on the left side of the equal sign, I'm only showing you one of the 13. And again, I'm lazy. I'm not going to write down all 13. So I'm going to add a subscript I. So y prime sub I denotes the rate of change of the ith neuron inside this 13 neuron CTRNN. Right? So I really have y sub 0 prime, y sub 1 prime, y sub 2 prime, and so on. There's 13 ordinary differential equations. We're just looking at one of them. So far, so good? Okay. What's on the right-hand side? In CTRNNs, the creators of CTRNNs built in a lot of biological detail to these neural networks beyond what you've seen so far. The first biological detail they're building in is this. Whether biological neurons actually show behavior that's continuously changing in time is a controversial subject in neuroscience. Some neuroscientists say, nope, a neuron sends a pulse of electricity to another neuron. That's a discrete event. You don't use differential equations, they don't make sense. Others say that's true, but neurons really emit chirps of electricity. Beep, 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 beep. That's picked up by the target neuron. And over time, all of that detail gets washed out, and you get more or less activation in the neuron. So some controversy about this in neuroscience. For our purposes, we're going to assume it's useful to have neurons inside the head of a robot in which the values are changing continuously. We'll see why that's helpful next time, and we'll develop the math behind these neural networks next time. We'll put a pin in things for now. You have a quiz due tonight. You're working on assignments 5, 9, and/or 10. See you next Tuesday. Thanks.